I thought to write down, like, make some useful equations for you, like the same thing that we had from chapter 3 to 6, but this time that one was I did by hand, but this one I made it like, I thought it's a good idea to have it like in a slides like this as a final slides, but it's just useful equations that you can, like, when you want to work on the quiz or when you are working on your assignments, you can look at them. Mostly they're equations, right? So when we say aliasing in the 1/2 fraction of 2 power 3, we say, for example, A is equal to BC, B is equal to AC, C is equal to AB. Aliases can be found from the defining relation as we had before. So you would say I is equal to ABC. It's just an example. And then you would multiply whatever terms that you are interested to find out the compounding pattern of it, or aliases, by the defining relation, and then you're going to find out the compounding pattern, the other one. In the textbook, as I said, we have this notation that we have a bracket like this, and then like for A, and then we write down like A is like equal to the A plus, for example, BC. So it means that here A and BC, they have their each other's aliases. We have it for B, we can have it for C as well. That was coming from the, like, for the principal fraction. For the alternative one, I is equal to minus ABC is the defining relation 2, implies slightly different aliases. So it's going to give you this one, but this one is for the alternate fraction. Both designs belong to the same family. In fact, if you add them, it's going to give you the full factorial, and the same family as defined by the I equal to plus minus ABC. I talked about this, like how many aliases per effect. So we would say 2 power P minus 1. P is the independent design generators that you can see in the design generator table as well. These equations are very good. We had it before in chapter, like end of chapter 6 as well, like with the useful equations that I gave you from chapter 3 to 6. I think it on page 4 of that cheat sheet of the equations that I gave you, you can find that most of it. So how to calculate, here is that effect, sum of a square, regression parameters, standard error, and confidence interval that we would have. For the effect, we would say it's contrast divided by divisor. So contrast divided by the R times 2 power K minus 1. For contrast, we would say Li by I. Li is the positive and negative one. It's the coefficient of design column. Like we would have the, when you have your design table, when you have all of those negative ones positive, so those are the Li, and then multiplied by the Y. For the sum of a square of the effect, sum of a square effect is the R times 2 power K minus 2, and K here is the number of the factors. And the effect power 2 divided by the degree of freedom. If you say divided by degree of freedom, it's going to give you the mean square, the same things that we had in ANOVA table. R is it's going to be the fraction, if you have like the fractional factorial or the complete replication of the full design. If you have partially replication, then you would consider R equal to 1 as well. K is the number of the factors in full design. Then before the parameters, we said that the beta null is the average, right? R times 2 power K is going to give you the number of the runs that we would have. And the sigma by I is whatever response that you have add them divided by the number of the runs that we would have. And for beta, whatever effect that you got, the square divided by 2. The standard error, we would when we want to find it, it's going to be the standard error of the effect. It's going to be the square root of the variance of the effect. For the variance of the effect, we have this equation. And then also we can say, because we said that beta is equal to 1/2, 1/2 of the effect power square. So we can say a standard error of effect is going to be 2 times a standard error of the B, like the estimate of that. I had a typo here and I just fixed it. So in your notes is the correct one. It's the half of the effect, not effect squared. So because of that, a standard error of the effect is going to be 2 times standard of the beta. You can use this equation for it. And then here you can have an interval for it. So we have learned that from like first chapter and second chapter. It's like whenever you have your standard error of some parameter, then you're going to find the number from a table, t-table most of the time, and then you would say, okay, whether estimate that you have plus minus that one. So here is this. So you'll find out your effect, for example, plus minus t, and then t-value from the table, and then this degree of freedom is degree of freedom of error, and times a standard error of the effect. So it's the same things that we had before. It's just that I thought it's good that if I remind you here. So that's all the equations. Like, I think we have more than this, but these are the main equations that we have, like the highlights of chapter 7. And some part of it is from chapter 6 as well.